Today we're going to learn about limits at infinity and the limits of those sequences. This is section 11.4. At the end of this lesson, I will be able to evaluate limits of functions at infinity, and I will be able to find the limits of sequences. So let's get started. Let's consider the function f of x equals the quantity x plus 1 divided by 2x. How do we evaluate this function at x equals infinity? Well, we have to remember that infinity is not a number, but rather a concept that describes the forever of numbers, meaning you give me a number as big as you want to. I will find you a number that is bigger than that number, and we can play that dance forever. As a result, we shouldn't be speaking of f of infinity equals infinity times 1 over 2 times infinity. This, it's not a number, so I can't get a number from this. So instead, we should be using our knowledge of limits and the language of limits to evaluate the limit of f of x as x approaches infinity. And it's going to look something like this. The limit as x approaches infinity of f of x equals the limit as x approaches infinity of the quantity x plus 1 divided by 2x. Let's look at this function graphically and see what it looks like at values where x is approaching negative infinity and where x approaches positive infinity. Let's see how this behaves. The first thing we're going to do is we're going to evaluate this function at the given values of x that you see over here on the left-hand side of the table that I put together. Okay, so the first thing we're going to do is we're going to evaluate f of negative 5. That's a negative sign there. And that equals negative 5 plus 1 all over 2 times negative 5, which is the same as negative 5 plus 1 is negative 4, and 2 times negative 5 is negative 10. And if I evaluate that, I get positive 0.4. Okay? Easy enough, right? I've chosen to do the additional values of x without you being there. I think you can do those on your own. I did want to go over f of 0 though. F of 0, quite simply, looks like this. 0 plus 1 over 2 times 0. 0 plus 1 is 1. 2 times 0 is 0. And what do we get when we divide by 0? We get jazz hands, which makes this undefined. Very simply. When I place the rest of the values of x into my function, I get the values you see completing my table. So now I can start to graph this. But before I do, let's look at some special things. First of all, when x equals 0, that is a special thing. Whenever I get undefined for the value of my function, that usually means I have a vertical asymptote. So I'm going to draw a vertical asymptote at x equals 0. So let me do that while I got you on pause. I'm hoping you can see that. I did it in blue. And it's not quite vertical, ever so close to being vertical though. And I did that just so that you could see it a little bit better. But that's going to allow me to make my graph now. So I'm going to do that. So I'm going to graph these points but let me put in my graph lines first. You will see that I put in graph lines for every other y value, or every other graph line in the y-axis. What I'm doing there is I'm saying that 2 squares equals each one. So Go up 2 squares, that's y equals 1. Go up 2 more squares, that's y equals 2. 2 more squares yet, y equals 3. And that's my y-axis, and this is my x-axis. For my x values, I'm just going to stick to a 1-to-1 relationship, meaning for every square in the x direction, x goes up 1. Okay? So let's do this. So -5, when x equals -5, y equals positive 0.4. So -1, 2, 3, 4, 5, up almost to 0.5, because 0.4 is just a little bit under 0.5, and I got a point right there. When x equals -3, y, or f of x, is just a little bit less than that. I'll put a dot right there. When x equals -1, y equals 0. When x equals -half, f of x also equals -1/2. And then when x is 0, my f of x is undefined. So my function's going to look something like that. Terrible artwork notwithstanding. And then the same thing goes over here. When x equals 0.5, y equals 1.5. When x equals 1, y equals 1. And when x equals 5, y equals 0.6, so 1, 2, 5, and 0.6 is just a hair up from 0.5. And I get something that looks like that. Very terrible, very terrible. But my artwork was never my strong suit. So let's take a look at a better representation of this graph, shall we? Like so, and you can see a much cleaner version of what I constructed on the previous page. Okay? Now, look at this very carefully. When I look at how this function behaves, there is a magic line that I managed to put in addition to the vertical asymptote, there's also a horizontal asymptote. Look at where it is. It's at y equals 1/2. This function will never go below y equals 1/2. So look at that. As x gets bigger and bigger in the positive direction, it will get closer and closer to 1/2, but never go below it. So we can say that the limit as x approaches infinity of f of x equals 1/2. And that also jives with our previous rule. This is an order 1 polynomial on top, and this is an order 1 polynomial on the bottom. And what I can do when I have polynomials of the same order in the numerator and denominator is I can divide the leading coefficients of each polynomial. The leading coefficient of the numerator is 1, and the leading coefficient of the denominator is 2, so I get 1/2. So let's evaluate the limit of this function. The function is 4 minus 3 divided by x squared. Let's evaluate this function as x approaches infinity. Now, remember from our previous lessons that if I have two things being added or subtracted from one another, and I'm evaluating the limit of that, I can simply split out those functions. So, the limit as x approaches c of the quantities f of x plus g of x equals the limit as x approaches c of f of x plus the limit as x approaches c of g of x. And in for the purpose of this function, f of x is 4, So 4 is the constant function at y equals 4. And g of x is 3 over x squared. That's g of x. And instead of adding, I can subtract and I get the same property. So I am going to, as you can see here, I am going to split these up into the limit as x approaches infinity of 4 minus the limit as x approaches infinity of the quantity 3 over x squared. Now, if x approaches infinity, does that change 4? No, it does not. So the limit as x approaches infinity of 4 is going to be 4. And if you don't believe me, graph it. And you will see that 4 is just a vertical line at y equals 4. And then I'm going to subtract the limit as x approaches infinity of 3 minus x squared. Well, think about this. As x approaches infinity, what happens to this function? Well, as x approaches infinity, the denominator gets bigger and bigger and bigger while the numerator stays the same. Matter of fact, as x approaches infinity, x squared becomes infinitely large. So anything divided by an insanely large number is going to be very, very small. As a matter of fact, it approaches 0. So the limit of those two things simply equals 4 minus 0, which equals 4. Let's look at something a little bit meatier. Here I have my function f of x equals the quantity negative 2x plus 3 all over the quantity 3x squared plus 1. And I'm supposed to find the limit as x approaches infinity of this function. Now I ask you, just by looking at this, can you tell what the function does as x approaches infinity? Because when I do look at this, I get negative 2 times infinity plus 3 over, that 3 is not very good, over 3 times infinity squared plus 1. Now, I know that I can't evaluate this function because infinity is not a number. Infinity is a concept, right? If you give me a number for infinity, I can always give you a number that's a little bit higher. So don't think of infinity as a variable. And think of infinity as a way in which math breaks. So we have to think about this function differently when we look at x equals infinity. And so I ask you, which gets bigger faster, the numerator or the denominator? And if you know one gets faster than the other, how much does it get faster? Does it balance out to a specific point, or does it just keep going? So those are all questions that cause us to have to try a different method. So I am going to erase this, and we are going to look at the rationalization method. And the rationalization method is going to, remember when we rationalized before, we multiplied numerator and denominator by the same number. And we chose to multiply by the same number in both the numerator and the denominator because we're effectively multiplying by 1, which, as we know, does not change the value of the function. So that's what we're going to do. Well, what's going to be in the numerator is 1 over x squared. And we'll go over that in a second. So we're going to use the rationalization method and multiply both the numerator and denominator by 1 over x squared. So I want you to do that and then pause the video and see what you got and see if it matches what I got. Okay? When we do that, we get negative 2 over x plus 3 over x squared. That's my numerator. And in the denominator, I get 3 plus 1 over x squared. So I distributed 1 over x squared to both terms in the numerator and to both terms in the denominator. And what you should see, if you are paying attention, you will notice that I can evaluate the limit of every single term in this fraction in both the numerator and the denominator as x approaches infinity. So we split this up. We simply look at the limit. We simply look at the limit as x approaches infinity of negative 2 over x plus 3 over x squared. Well, as x approaches infinity, negative 2 over x, well, that just becomes 0. Remember, any number divided by an insanely big number is going to approach 0. Now, the main difference between a positive number and a negative number being divided by infinity, they both approach 0, but a positive number divided by a variable approaching infinity approaches 0 from the positive side, whereas a negative number being divided by a number approaching infinity approaches 0 from the negative side. But the limit as x approaches infinity is still 0. Similarly, the limit of 3 over x squared as x approaches infinity is also 0. Okay? So the value of my numerator is 0. The value of my denominator, 3, the limit as x approaches infinity of 3 plus 1 over x squared. Well, the limit of 3 as x approaches infinity is 3, and the limit of 1 over x squared as x approaches infinity is 0. So the value of my denominator is 0. So the limit as x approaches infinity of f of x equals 0 over 3, which equals 0. So let's look at that written in something other than my chicken scratch. And you'll see, and here in green, I got something that I want you to be mindful of. The trick is to make the denominator a number. So I told you I was going to tell you why we decided to choose 1 over x squared. It's because if I choose 1 over x squared to multiply both the numerator and the denominator by, it's going to turn my denominator into a number. In this case, my denominator became 3 instead of turning it into something times infinity or something times 0. So that's why I chose x squared. Now, let's try a different type of problem. But before we do, let's look at sequences. If you remember, when we were in algebra, we defined a sequence as a list of numbers that follows a pattern. We're going to call that our young person's or our kindergarten version of the definition of sequences. We're going to institute a new, more nuanced version, and that is a sequence, or an infinite sequence in this sense, is a function with the domain of the positive integers, including 0, and we got a special name for those numbers. And we call that the set of natural numbers. And you'll see it written as this funky looking n right here. Okay? And you'll also see it written like this like that. You'll see it written like that sometimes, okay? So let me get rid of that. And now you'll see n is an element, small n right here, is an element in the set of natural numbers, okay? So n could be 0, it could be 1, it could be 2, it could be 3, but it can't be anything in between those numbers, okay? Oh, I used the wrong thing here. Let's get rid of all this chicken scratch, and we will get started. Now, if you look at right here, A1, A2, A3, and then I got the dot, 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 and then all the way to A sub n, right? And then continuing on after that. Now, these are terms in that sequence. A to the n is the nth term in that sequence. If the sequence only consists of a finite number of terms, then we have a finite sequence, meaning there's an ending to it. Fair enough? Let's move on. Now, the nice thing about this is functions do a good job of modeling sequences. Furthermore, we can use our understanding of limits to evaluate sequences as my n approaches infinity. So if f of x is a function acting on the domain of the real numbers, remember, real numbers are all the numbers that we've considered. It's the positive integers, it's the negative integers, it's 0. It's all the rational numbers, meaning numbers that can be expressed as a fraction of two integers. It can be irrational numbers, like the square root of 2 or the square root of 5. It could also be the transcendental numbers like pi and e. Okay? Real numbers incorporate all those things. Now, f of x works on the domain of the real numbers. However, a sub n works on the domain of the natural numbers. So 0, 1, 2, 3, 4, 5, and so on. Only whole numbers from 0 on higher can be in the set of natural numbers. Now, the translation to this whole list of stuff that I got here is that we can treat a sequence in exactly the same fashion that we treat a function. And that's a beautiful thing. Let's see how. So, we're going to evaluate the limit of this sequence as n approaches infinity. So, the sequence is defined by a sub n equals 2 times n plus 1 all over n plus 4. So, who remembers the rules of finding limits of rational functions? If the order of the numerator is the same as the order of the denominator, the order of the numerator here is 1 because the highest power in this polynomial is n to the first power, and in the denominator, again, the highest order or the highest power of n is 1. So both the numerator and the denominator have order of 1. So if the order of the numerator is the same as the order of the denominator, then the limit is the same as the quotient of the coefficients, meaning the limit as n approaches infinity of a to the n would equal the coefficient of n in the numerator, and the coefficient of n is 2, over the coefficient of n in the denominator, and the coefficient in front of that is 1. So, the limit as n approaches infinity of this function is 2. And let's take a look at that written a little more clearly down here. The limit as n approaches infinity of a sub n equals 2. Now, this one is a little bit trickier, and you're going to use the rationalization method to come up with the answer. So pause the video and work out the limit of this function as n approaches infinity using the rationalization method. So, what did you choose to multiply both the numerator and the denominator by? The limit. The limit as n approaches infinity of a sub n equals 2n plus 1 over n squared plus 4 times. And we go 1 over n squared times 1 over n squared. Just like that. We're multiplying both the numerator and the denominator by 1 over n squared. And then I get 2 over n plus 1 over n squared. I simply distributed 1 over n squared through both terms in the numerator, and I'm doing the same thing to the denominator now, and I get 1 plus 4 over n squared. And if I simplify that, now I can use direct substitution. I can plug n into each place. So now I got 2 over infinity, well that becomes 0, plus 1 over infinity squared, that's also 0. And then in the denominator, as n approaches infinity, 1 just remains 1. And then 4 divided by infinity is 0. So this equals 0 over 1, which equals 0. And 0 is my answer. Again, pause the video and work this one through. Find the limit of a sub n as n approaches infinity. And you will find that to evaluate this, over n cubed times n plus 1 times 2n plus 1 over 6. And we're going to, first of all, before we get into rationalizing this, we're going to simplify. And we're going to say, well, we're going to multiply this through. 8 times 8n times n, 2n squared plus 2n plus n plus 1 all over 6 n cubed. So I multiplied 8 times n to get this. And then I multiply n cubed times 6 to get 6n cubed in the denominator. Now I'm going to distribute the 8n through to every term in the numerator. And that's 16n cubed plus 16n squared plus 8n squared plus 1 over 6n cubed. Now I can simplify by adding these two terms together. 16n squared plus 8n squared is 24n squared, but I really don't have to because I have polynomials of the same order in the numerator and the denominator. The highest order, or the highest power of the polynomial in the numerator is cubed. I got n cubed in the numerator, and I got an n cubed in the denominator. So the limit of this is simply 16 divided by 6. And if I simplify that, that becomes 8 thirds. and 8/3 is my limit of this function as n approaches infinity. So, at the outset, we told ourselves that we would be able to find the limits of functions at infinity, or more specifically, the limits of functions as the variable x approached infinity, and we could also find the limits of sequences, again, as the variable, in this case n, approaches infinity.